Okay, so today we are going to discuss about the topic about deep sequence models. Right? Uh, so before that, we have discussed about feed-forward neural networks, basically the single layer perceptron, the backpropagation, and the theory behind it. So how it is learned, and we have referred the uh, theory that we have learned about machine learning as well. So that's a requirement for learning deep learning. So then we have learned about convolutional neural networks, which is about modeling the spatial data, right? Spatial data in the sense when the data is basically located in the 2D space or something as pixels, you can use some filters, so and you can identify, you can model the content, the meaning of the image using convolutional neural networks. Today's session, we are going to discuss about sequence models. So that is not really about the spatial models or feed-forward models. That is also a different form of machine learning modeling. So that is mainly about temporal modeling. Temporal modeling means how are we going to model a sequence of events with machine learning, right? Uh, so what are the sequences that you see in day-to-day life, right? So not the sequence what you see, right? So what the things that are important to be modeled with machine learning. So what are the things? So suppose you are making doing some trading. That means you are trying to get some profit out of trading in the financial markets like a gold market. You can find the price of gold, how it is varied with time, right? So this the price of the gold with time can be, or some if the gold price is not fluctuating, you can think about the price of Bitcoin, right? So how it is changing, right? So these kind of parameters, the price of cryptocurrency or price of gold is going to be changing. It's changing time to time, right? So those are sequences of events, right? So in each minute or each second, you see that the price of this commodity or the cryptocurrency has changed. So if you can model it, then you can forecast the future price of cryptocurrency or gold, right? And suppose you are uh, watching some football play, right? Football match. Uh, if you so there's no practical requirement, right? So but if you are trying to model a video game or something uh, with soccer, you can predict the future position of the football using some, either you can use the mathematics, the analytical mathematics to find the next position of the football after a certain time, like after the next second, what would be the position of the football with the velocity vectors of the football and the air speed and the air resistance, the power speed of the speed of the football and so on. Or you can use some machine learning model to find to find the next position in the of the football after the next second or the next few milliseconds or something, right? That means you can do it analytically using mathematics, or you can use some machine learning models to find the next position. So finding the next position, say like after 100 milliseconds, is like finding a sequence of events, right? So you can consider them as sequence of events as the which is the position of the football in the three-dimensional uh, soccer game, right? So that is also a sequence of events that you are trying to model. And if you try to find the, say like you are trying to give the treatment to a patient with diabetic, you have to need to find the future blood glucose level of that patient so that you can give insulin or some medication to control it, right? So that is also a sequence of events, right? So the blood glucose level in each of the time, say like after each of the hour, you can find, if you have a model to predict it, then you can use it that model to treat the patients. And in genetic engineering or bioinformatics, you might have, if you have learned it, you may know it, right? In order to predict the or like create new genes and do some genetic modifications and DNA sequence editing, you should be able to process the DNA sequence with some model. So right, so maybe in these days, machine learning is the one that is using heavily for genetic engineering, for editing DNA sequences. Right, so that is another sequence modeling requirement. And if you are trying to develop a self-driving car, you have to find what are the driver actions that you have to take, like whether you should turn right, left, or you press the accelerator or the brake or whatever, right? So those are sequences of events that you have to model with the machine learning model or some other non-machine learning system, right? And also when it comes to understanding the language of a text, right? So that is a task of natural language understanding. In that kind of task, you are considering the sequences of words as a sequence model, so that you either you can understand the meaning of that particular sentence or the paragraph, or you can get summaries out of the paragraph, or you can fill the missing words, or you can get the sentiment out of the paragraph, or something like that. So for that, you can take the sequence of words as a sequence of events and model it using a sequence model, and then you can get the advantage of making systems for natural language understanding, language translation, and so on. And also when it comes to speech recognition, so what happens is what we say in with sound, right? With our mouth is a set of frequencies, right? So if you could sample the frequencies that I say in each 100 milliseconds or 10 milliseconds and so on, and you can find the distribution of frequencies and the amplitudes in each time step, right? So that is also a sequence of events. With this sequence of events, you can identify what I have said. So you can use a speech recognition system, and you can give these frequencies and each of the amplitudes and give to the model as a sequence of events. And then you can model, so what I have said, whether I am in the, what is the mood that I am in, whether I am trying to tell something, or my tone, my what I have said in literally, all those things that you can do with speech recognition. And that is also an application of it's also an application of sequence modeling. So for each of these scenarios, you don't have to build different types of machine learning models, but you can use common set of sequence modeling techniques that are available in machine learning, so that you can use those models to achieve these kind of requirements, right? So with deep learning, the sequence modeling can be achieved easily. Easily means with high success rate. So that is why the deep sequence modeling is getting popular, right? So most of the things, for example, if you are writing something with handwriting, so the movement you make with your pen is also a sequence, right? So how you move your pen when you are writing. So that can also be modeled as a sequence model. Then that can be used for handwriting recognition. Right? So there are many applications like that. You can use the sequence modeling that you might not have even thought about, like robot arm movement, the uh, movement of the water levels in the sea or something. Many problems that we think that are impossible to model can be modeled in sequence modeling tasks. So here we are going to learn the deep sequence modeling, which is an application of deep neural networks. Right. Right. With the earlier knowledge we have learned, mainly with feed-forward neural networks, what you can do is you can give some input X to the neural network, and then you can get some output, the prediction Y hat, right? That is what we do in independent events. Independent event means, so for example, if you have land to sell, then you have this land value, the distance from the main road and all those parameters as X values, and then you get the price as the Y hat, which is the output, right? So that is only for a single event, single specific land or something, right? But suppose you have a sequence of events, not just a single event like this. So then uh, this Y hat or the predicted value is not only dependent on the input X, right? For example, say that you are you are doing some natural language processing tasks, right? Like you are analyzing a set of words using uh, using a sequence model. So this is not a sequence model, right? So this can be achieved with the feed-forward neural network easily, because this is only relevant to a single event. But when there are multiple events, like predict in the as have discussed in the previous slide, then the requirement is that the predicted value or the Y hat should be dependent on not only on the input xt, but on the uh, state that was there in the previous time step. Right? For example, suppose that you are trying to uh, model. So I will not take the natural language processing example, because then you may have some problems how to do it, right? So say like you are trying to find the movement of the football, right? So here you, as the X, what you do is you give the uh, current velocity vectors of the football, right? So X, in the X side, what is the speed of the football? In Y direction, what is the speed of the football? And the Z direction or the depth, what is the speed of velocity of the football? So all of them are velocities, right? Because velocities are vectors, right? So with all these vector values, you can predict it. But if it is moving with some other parameters, like with say like there's wind is blowing, and there's some rotation which has some drag with the air or something like that, which has a time series requirement, uh, dependent, right? That means not only with the current uh, values, but with the previous state. Then there's a hidden state component uh, that can be considered as a dependency for this uh, sequence model, right? That means unlike the earlier case where you can just predict the prediction with the input, but now you have not only the input, but the hidden state of the previous time step as well. Right? So when you predict this Y2 hat, you are not dependent not only on the x2, but with the hidden state of the previous time step, which is h1. So when you are predicting the earlier timestamp also, which is y1 hat, so it is not only dependent on the x1, but also the previous hidden state, which is h0, right? So this is how we have created the first timestamp. There is no hidden state, so we can just use the input value to predict the y hat 0. But after that, in each time step, you have to bring forward the hidden state of this system, and that system, this value, this vector, can be used as an input along the real input to make the predictions, right? So in this timestamp, we are not only using the x1, but the h0 as well, the hidden state of the previous time step as an input to make the y1 hat prediction. So when you are making the y2 hat prediction, we are not only dependent on the yx2, but the h1 or the previous timestamps hidden state as well, right? So this can be denoted like this, right? So yt hat is a function of input xt and the past memory or the hidden state of the last time step, which is ht minus 1. That is the predicted value. So when you are running a sequence model, you can model the system like this as a sequence of time steps, or you can use a single unit like this, where you can use we can name this as a recurrent cell, and the ht is used as a feedback, not a feedback, it's moved to the next time step as the output, as the hidden state, so that the next time step can use the hidden state of the previous time step and make the predictions. So this model can be simplified or summarized into this kind of notation as well, right? So I have just given this notation so that you will understand when you have a system like this, then you can make a prediction not in the same way, but these two are the same, right? So this is a summarized view. This is the view that we can understand, right? So if you think what is there in this green color neural network, so mainly this may be a single layer neural network, right? So where the x is multiplied with w, right? So like wtx plus b or something like that, right? So which you already know, right? So then you can apply the attention and activation function, and then you get the yt. So in these blocks also, you can think something like that, right? So let's see what happens. So first, let's see what can we do with these kind of sequence models, right? Say that I said that sequence models are useful for making many types of different applications, right? So, but in this case, you can categorize the sequence model into mainly into three, right? So many to one, one to many, and many to many. Right? What does it mean? It's like this. Say now you have many to one. Many to one means you give many x inputs. That means you give a sequence of inputs, and you are trying to predict a single output. So there are many xt values, x1, x2, and x3, and you are trying to predict a single y hat value. So that is a many to one model. So here what happens is the first x value is generating some output, but this output is not used, but the hidden state is moved to the next state, and the next input is given, and the hidden state from this state and the input is used to make another hidden state, and the new input, the third time steps input, is used for is used as the input, and the input from the previous time step is also used to make the final prediction, which is a single y-hat, right? So if you take an example, so if you want to do sentiment classification, this is an example for this many-to-one sequence model. Say that you have many word tokens given as x1, x2, and x3, and so on. When you are trying to analyze the sentiment of a paragraph, right? So what you get as y-hat is whether the sentiment is good or bad, right? Whether the person is happy or unhappy. That is the output that is predicted by this model. So there are multiple inputs for multiple words, and you get a single output, which is the sentiment of this text. So this is known as a sentiment classification problem. So if you consider a sequence model where there are many-to-one, like image caption, right? You give the input image, which is a large image with many pixel values, right? So we will see. So this is not exactly correct, because generally we are not processing large images with these sequence models, but just say like, right, you are using image, then you make some output, and the hidden state is also moved to the next time step and make another output y-hat 2. This is y-hat 0, y-hat 0, y-hat 1, and then the hidden state is moved to the third time step, and y-hat 2, the third output is created. So here what is happening is, after you have given the image as the input, you are having multiple words as the output, which is the caption of this image, right? So when you want to caption this image, you give the image as a single input, and then you get a sequence of outputs, which is relevant to the sequence of words of the caption of this image, right? This is an example. So if you consider the many-to-many sequence models, so the best example is that you can use machine translation. Machine translation means you, like with the Google Translator, you can give some input, say with the Chinese as the input words, and you can get some output words in English, right? So you give multiple inputs and you get the multiple outputs, right? So the same hidden state is moved like this, and the outputs are given like this. These are the inputs that are given to each of the time step. So, right. So you may think that that how does it happen? So we will discuss it later. How these images, how these texts are converted to these input vectors, right? So we will discuss it later. For now, just think that these are some sequence model, deep sequence model units, right, for each of the time steps. So one of the basic or the fundamental units that we learn with deep sequence modeling is known as recurrent neural networks. So that is the simplest form of deep sequence model unit that you can learn, right? So, but actually these recurrent neural networks in its pure form are not used in practice to do all the sequence modeling tasks, but we will learn them later, right? So, but for the learning purpose, we are going to learn about recurrent neural networks, or RNNs, to learn about the sequence models, sequence modeling units, because they are easy to learn, and because this is the most primitive and the oldest form of units that are used for deep sequence learning, right? So this has the same. So this is the notation that we learned earlier, right? So this notation, this recurrent cell is there, the hidden state is moved back into it for the next time step. There's the input and there's the output. So this is the RNN unit. We give the input, which is the input vector. And we get the output y hat t, which is the output vector. After each of the time step, you provide some hidden state ht as the output, and it can be used subsequently in the ht plus 2, t plus 1 time step with the same RNN, right? So make sure that this RNN has some set of weight vectors, like with this, all the other deep learning models, right? Neural networks, we have some weight vectors in this RNN, and those are used to make the prediction of y hat t. So all the time you see that there's a t as the suffix. That means when you are defining the RNN or the recurrent neural networks, you have to specify the time step of this operation, right? So for the generic time t, we define the RNN as this, like this, where we give the xt that at the t time step, what is the input, and we get the y hat t, which is the predicted value for the t time step, and you get the ht, the hidden state of after the t time step, which is used as the input for the as an hidden input for the ht plus 1 time step, right? So these are the some of the base, I would say it's a kind of simplified form of notation that you can use for, excuse me, for representing a recurrent neural network. So the input vector is as xt, like you already know, right? So like we have learned from the beginning of this lesson, xt is the xt, right? So then what happens is, then you multiply this xt with the wxht. So this t is for this transpose, right? Transpose in this w vector. So we have in this recurrent neural network, there is a weight vector known as xh, right? wxh, w suffix xh. So we take the transpose of this vector and do the multiplication with this xt for the input, and then we add with this or concatenate with this another input, which is the hidden state input from the last time step, which is ht minus 1, right? So when you give the input ht at the time step t, you get the ht minus 1 from the previous time step, right? So suppose now, so this is the time step t, right? So where you get the input t and you output the y hat t. So you get the hidden state from the t minus 1, ht minus 1 from the previous time step, which is this is the hidden state. And then we have another weight vector in the RNN, which is known as w suffix hh. So we take the transpose and take the linear combination, and then we concatenate it. So that this is how we get the linear combination of from in both input and the hidden state, right? So actually, you need to add another bias term as well. So, but for the simplicity, we haven't included the bias term in this notation, right? So then we apply the activation function, like in the ordinary neural networks, right? So generally, the activation function used in RNN are tanh functions. So this is the hidden state that is generated at the timestamp t, is ht, right? So the tanh of concatenation of these two, addition of these two values, right? So when you have generated the ht or the hidden state, then you can generate the output y hat t by again taking a multiplication with the transpose of another weight vector defined in RNN, which is W suffix HY. Right, so now just look at the highlighted weight vectors in the RNN. Right, so first you have found. So there's a weight vector for to be multiplied with hidden state, the previous hidden state, which is WHH, and there's another weight vector defined here to be multiplied with the input, the current input, which is WXH. And there's another weight vector defined in RNN, which is to be multiplied with the current hidden state to generate the output, which is WHY. Right? So there are three weight vectors that are defined in RNN, but make sure that, and also note that in this W vectors, you don't see any T term in it, right? So not this capital T. So this capital T is for transpose, right? For transpose in the vector. But there's no simple T notation in any of the weight vectors. Right? That means these weight vectors are common for this Rn. That means that is these weight vectors are common for all the T values or all the time values, time steps for this RNN, right? So with T equals 1 for the time equals 0, 1, 2, up to T, all the values, for all the values, these W vectors remain the same, right? So they will get updated, so they will be used, right? But those values are the same in for all the time steps of the RNA. So that is something special that you have to remember, right? Although we think this as a layered architecture where we at each time step we multiply with each of them, but still these weight vectors are not getting changed from time step to time step, right? So these weight vectors remain the same for all the time values for this RNA. That is something you have to understand. So this is what we have mentioned. So there are three vectors WXH, WHH, and WHY. The tan H is the activation function that we are generally using. And then we maintain the hidden state and we multiply with this output vector and get the output value. And these WXH, WHH, and WHY are common for all the time steps. So now let's look at how the recurrent neural networks are trained. So in this lesson, we have not discussed about the loss function because generally the cross-interrupt loss can be used here, but because we have much to learn with these RNNs and sequence models, we are not going too deep about calculating the loss and so on, but because it can be easily calculated. Right. So what we are trying to do is understand how the basics of these sequence models. Right. So when it comes to RNNs, right? So like this, for each of the time steps, these outputs are generated, right? For each of the outputs, so there is a real value or the ground truth value, and these are the predicted values, right? So for this y hat 0, that's a y0 as well, which is the ground truth value. For this y1 hat, there's a y1 value as well. Is the ground truth value. The difference between these two is known as the loss, right? So when you want to calculate the total loss for this single pass, you can add all these losses and then you can find the total loss and take it as the loss for this recurrent neural network. Right? So how you calculate the loss is that you calculate the losses for each of the time step, and then you add all of them, and that is how you calculate the loss for this RNA. Right? It is something like this. Right? So this is the summarized diagram, and this is the expanded diagram. So as the common notation, so this is the forward pass or the forward propagation denoted by black lines, right? And how the weights are updated, the gradients are updated. So that is defined by the red backward pass or the back propagation direction, right? So what happens is these weight values are there, which is common for all the time steps, as I have mentioned earlier. For example, WHY is common for all the time units. WHH is also common for all the time units, and the WXH is common for all the time units. Right? But X0, X1, X2, XT inputs are changing, and the predicted values are changing. So the losses are also changing. L0, L1, L2, L3, and those kind of different losses you can get for different predicted values. And by adding all these loss values, you can get the total loss. The total loss can be used for as the back propagation. With the propagation, you can propagate the loss for each of these time step units, and from these time step units, you have to propagate the loss back through the time. So this is known as the back propagation through time when it comes to RNNs, because unlike in the ordinary neural networks, when it comes to RNNs, because there's a time-related dependency with each of the time step, the gradient should be updated in the backward direction of the time, as shown in this red lines, right? As well, because of that, that is known as the back propagation through time. So these values, these loss values are propagated through the time steps backward up to the beginning of the time to update the values, update the gradient values, right? This is how the RNNs are trained. Here we can see that compared to the previous neural network types that we have learned, these RNNs are deeper in nature, right? Because we are trying to actually, what the purpose of the RNNs is to predict a sequence of events, right? So when you want to model better, you want to have many number of time steps, right? So in this, because of that, then the number of time steps are getting increased compared to other neural networks. So in other neural networks like feed-forward neural networks and convolutional neural networks, the depth is increased so that we want to increase the accuracy or increase the intelligent level of the neural network. Right? But when it comes to RNNs, if you want to model a time step to model with many number of time steps, you have to increase the depth of this recurrent neural network. So this is not known as the depth, really the depth, right? So depth is something else that we will discuss later, but the depth across the time, right? That means the number of time step units have to be increased with the number of time step that you are using. So because of that, RNNs are getting much more deeper compared to the other neural networks types. So because of that, especially for the RNNs, these problems are significantly observed in RNNs, like exploding gradient and vanishing gradient problems. As we have discussed earlier, we can use gradient clipping to to address the exploding gradient problem. And for addressing the vanishing gradient problem, you can use some activation functions like ReLU activation and value weight initialization like identity initialization. So which we have not much discussed previously, right? But what we are doing is we are initializing the weight vectors as 1 values and biases as zeros. So if you are interested, you can search this and see, right? So that is one way of initializing for the RNNs, initializing the weights for the RNNs. And also there are better modified versions of RNNs, recurrent neural networks that you can see that people have invented, known as LSTMs and GRUs, which are designed to address the vanishing gradient problem. Okay? Not only the vanishing gradient problems, so there are some other problems as well, which they were designed to be handling. So we will discuss these two as well, how they are defined and the purpose of these new innovations of new developments of the recurrent neural networks. So these unit types are much more complex than pure recurrent neural networks, but they are very good at doing the real world sequence modeling tasks compared to RNNs, because as I mentioned earlier, RNNs are not really useful at most of the practical scenarios like natural language processing, because its inability to uh, keep the sufficient amount of history in its hidden state. Right? So we have learned that with recurrent neural networks, we can have a hidden states which keeps its history in it, so that it can maintain this information in the hidden state, which are used to make predictions. But with recurrent neural networks, this hidden state mechanism is not that advanced, so that with the number of time steps, the values in the history are getting exponentially decayed. Because of that, RNNs are not that good at keeping long-term memory. Means it can't say like keep the memory of hundreds of units, time step units, memory in it, so that you can use it later. Because with RNNs, after a certain few number of time steps, the history value or the history memories are getting forgotten or getting erased from the hidden state because of its function, due to its nature function that is used for in RNN. So right, so this is the function that they are using, right, to calculate the hidden state, as we discussed earlier. But this is not good when it comes to keeping a long-term memory. So when you are doing the real world task, we have to keep some long-term memory, right? So even in humans, we have to have long-term memory to make decisions, right? So we have to remember what we have said earlier. Say like we are reading essays, say that my name is Manind and so on. So if that is the case, so when I say something about my name, you should remember that I said earlier that my name is Manind. So Manind is the author of this text, right? So you have to keep those kind of important stuff in the memory, the long-term memory, when you are going through a text. But when it comes to RNNs are not good at keeping those kind of long-term memories. So, but these improved versions of RNNs are good at keeping these long-term memories in it. So that is another advantage of using LSTMs and GRUs. So we will later look at their implementations as well. So this is the backpropagation and time with RNNs, and let's see a simple, not a simple, but a commonly used, a widely used example for an application with recurrent neural network. So actually, this is also not a real example. So in real applications with this language modeling, not the pure RNNs are used, but the GRUs or LSTMs are used instead. Right? So for the learning purpose, let's say that language modeling is a RNN application. Right? So let's see. So if you haven't learned about natural language processing, so let's see how we are trying to model this language modeling, and what is language modeling, and what we are going to do with recurrent neural networks. Say that you have a text, right? Something like this. Capital of Sri Lanka is, and there's a blank. That means you have to fill the last word of this text. You have to fill the last word of this text. This is the requirement. So when you are good at language, that means when you have gone through many amount of texts, right? Like not not little big, but say like petabytes of data of text, and then you have learned your machine learning model with that amount of text. Then your model will have some understanding about the language, right? Not only the English language and its grammar, but also the common sense, like what is the capital of Sri Lanka, right? It's Colombo in general, right? Just forget about Sri Javadrupakote, right? Say like for now, just assume that the capital of Sri Lanka is Colombo, right? So when it comes to a language model, it should be able to predict that the Colombo is the missing word in this text. So completing the last word, or the predicting the probability of predicting the word token that should come at the end of this text, is the task of language modeling. Right? So what is language modeling? Language modeling is basically completing the last word of a string. Right? So that is language modeling. I have used this RNN application because this language modeling is the most widely used AI technology these days, with all these chatbots and ChatGPT and all those things. So which is known as the large language modeling, which is a scaled up version with different technology. But still these theories are applicable. So that is why it is important to learn about language modeling, the theory behind it, and how it is working with, how it is implemented using uh, sequence modeling units. Right? So the requirement of this machine learning model is to fill the last word as Colombo. Right? So how to do it? So the problem, if you say now you don't know anything about natural language processing, so what you are going to do? You may be thinking that you can use these terms as the as the inputs, right? And then you can uh, predict the last token. But the problem is that for a neural network, you can't give a text input or generate text outputs, because neural networks can only process numerical data like vectors. Right? So you have to convert these word tokens into a vectorized form, so that the neural network can process these vectors and generate some other vectors. You have to convert these generated vectors back into the word tokens. So you should know a way to convert in between word tokens and these vectors in order to process these words or the language texts using neural networks. So now let's see how we can convert a word into a numerical format. So say that now this is the uh, string that you want to convert. The first thing that you have to know is, I don't know whether you have learned. First thing you have to do is once you get a string like this, you have to do an operation known as tokenization. So in tokenization, what you do is you split this string uh, by some splitting tokens. In this case, it is the space token, right? In between all these words, you can see there's a white space. So now you can split this string by the white space, and you will get a sequence of tokens like this. Capital of Sri Lanka is, now there are 5 tokens, right? So from this string that now you have got a list of 5 tokens, right? Now what we have to do is, for each of these tokens, we have to assign a value, a numerical value, right? One way is that you can have a vocabulary, right? Vocabulary means something like a dictionary where you alphabetically order all the terms that are there in this language. Say like it starts from A, B, C. C we have capital, E, H, I. There's is, O, I, J, K, L, M, N, O, of, and so on. Sri Lanka and all those terms. We can have some numerical value. You can apply. You can have a numerical value for each of these tokens in your vocabulary. So vocabulary is something like a table where you have each of the terms or the vocabulary words and a respective uh, numerical value, which can uniquely identify that particular term. So that is one way of converting a word into a numerical value. But if you can remember in the machine learning module, we have learned that you can convert into words into this kind of numerical form, which is known as label encoding, right? But the label encoding is used only when there's when the tokens or the variable, so in this case the word tokens are the variable, these tokens should be in the ordinal data type. So what is the ordinal data type? It is something like it should be categorical, but categorical means those should be not be values. So those are tokens, but they should be having some order, something like alphabetical order or something, some low to high value order. But when it comes to the meaning of these terms, there's no particular order, right? So it is not correct to use this label encoding for representing these terms, right? Because there's no particular order. So why? So that means these data are not ordinal data. So the example for ordinal data is the t-shirt size, right? The t-shirt size should be small, medium, large, XL, XXL, and so on, right? So when it comes to these kind of ordinal data, so there's size increase with the number of sizes. Because of that, for the small, you can have 1, medium, you can have 2, large, you can have 3, and so on. But when it comes to words like this, it's not correct to give some numerical value where these numerical values have no real sense when it comes to processing these tokens. So it is not good to represent these tokens with label encoding. So this is not correct. So the other way of representing this kind of tokens is using them as by considering them as categorical variables. Categorical means they are just variables, but there is no ordinal value. They have just the nominal value. So what you can do is you can use one-hot encoding for this kind of tokens for converting them into vectors. So if you can't remember how the one-hot encoding works, so it's like you have for each of the, like in the label encoding, suppose now you have 1,000 words in the vocabulary. So you have started from 0 to 999, and only in a certain time in the certain index you have 1, and you have a vector like this. For example, in one-hot encoding you have a vector with the dimension 1,000, and only in one location, where the index is 34, there's only one symbol, right? One token in the one value in only a single location in this 1,000-dimensional vector is relevant to the word capital. For the word off, the index should be 567. So the 567th index is 1. All the other indexes are 0. From 0 to 999 locations. For the tokens 3, the index 734 is 1. All the other indexes are 0. For the Lanka, 56th index is 1, and all the other indexes are 0. For the word is, only the 346 index is 1, but all the other indexes are 0. So these are the one-hot encoded vectors for each of these words, right? So now the problem is that now the representation is correct, because those terms doesn't have to be ordinal, but they can be categorical as we wanted. But now the problem is that these vectors are too large, right? And they are very, very sparse. So what do I mean? Sorry. They are very, very large means, so this dimension of this vector is 1,000, right? So in order to represent this capital term, we have to maintain a 1,000-dimensional vector. But only one index is 1, having the value 1. All the other locations are 0. So this is known as extremely sparse indexing, right? Sparse, very sparse vector. So these sparse vectors are sometimes difficult at computation, and also in most of the cases it is very difficult to do the computation because of the memory and processing requirements. Because suppose there are several words like this, the memory requirement for keeping these vectors is very large, and it is very difficult to process, to do the vector calculations when the vector size is too large. Generally, the vocabulary is generally like 20,000, 30,000, 50,000, and so on. So when you have this long vector for a single word, it is very difficult to do the processing. So that is why the one-hot encoding is not suitable in practical use cases. So what we have to do is we have to use a much smaller vector where the sparsity is not there, but which is known as the dense vectors, like this. So the common way of finding an alternative form of vectorization for the word tokens is known as word embeddings. Right? So in word embeddings, we don't have the sparse vectors like all the other locations it's 0, and there's only one location, there is 1, and so on. We have a limited number of dimensionality, and each of the dimension there is some value. So this is the nature of word embeddings. So the word embeddings are the advanced version of word token vectorization. Right? So this example, if you haven't learned about word embedding, so in this example you can have some understanding how the words are given a vector, right? So say that now you have terms like cat, kitten, dog, house, man, woman, king, and queen. So those are the words, right? So now you are trying to find the vectors for each of these words. So what you are doing is, it's not like you are having a vocabulary and then you are putting an index uh, for one at the each of the thing, each of the token, like in one hot encoding. But here, what you do is you measure each of the token, each of the words in certain measures, like whether it is a living being. The token is a living being. So you know the cat is a living being. So it is 0.7, 0.6 times probability we can say it's a living being. Kitten is also a living being. Dog is a living being. Houses is a living being, but it's not a living being, but some due to some incorrect nature, the houses, it should be horses, I guess, right? Should be horse. It is also a living being, right? Man is a living being, woman is a living being, king, queen, all of them are living beings. So those are having positive values. Then there's a feline, and so we will not explain this one. So, and there's another way of measuring known as whether it is human. So the cats are not humans, right? Because of that, it got positive small value, 0.1 plus 0.1. The kitten, we got a negative 0.1, which is negative value. Dogs are not human, but because they are very close to the humans, it has got a bit higher positive value, right? So these houses are actually not houses. This is the word correct, right? Houses are not humans. Because of that, it has got negative value. Then man is a human, got positive 0.8. Woman is a human, positive 0.9, and so on. King, queen, all of them are human beings, so they have got a very high positive values. And for the gender, so we can classify these terms with gender as well. So the cat, uh, you have certain gender, right? For kitten, the gender is kind of maybe it's maybe if you can have this gender wise gender value, like higher the value, it may be more about masculine gender, right? So when the the cat may be having a higher gender and the kittens are very innocent because of it has a lower value and so on, right? And these houses don't have a gender because of that he has got a less value, something like this. And the women are female, because of that they have got a negative value. Queen is negative because queen is also female. Man and king have got positive values because they are masculine. And royal, then you can measure with another parameter like royalty. Like cats are not royal, they are just animals, negative. Kittens are negative, dogs are negative, houses are negative because those are not royal values. Uh, Men and women are not also not royal, but kings and queens are highly royal. Because of that, they have got positive 0.9 and positive 0.8 and so on. And whether it is a verb, whether it is a plural or singular, based on those kind of properties, you can categorize, give some values for each of these terms, and then you can create a vector for each of these terms and use this vector to represent that particular word instead of using a one hot encoded vector. Right? So this is known as a word embedding. So in this case, there are dimension of 7, right? So 1, 2, 3, 5, 4, 5, 6, 7. Dimensionality of 7 for the vectors, but with some dimensional reduction techniques like 2SNE, and so on. So there are specialized dimensional reduction techniques for especially designed for this word embeddings. And so there's a technique called 2SNE. So with these techniques, you can reduce the dimension from 7D to 7 dimension to 2 dimensions. Right. So this one dimension, and this is another dimension. So these vectors are also reduced with dimensionality. So when you have reduced the dimensionality of word embedding, now you can see that similar tokens are grouped together, right? Houses are not living beings, so because of that, houses are away from these three, right? Cat, kittens, and dogs are away from houses, and cats or kittens are of the same species. They are more nearby. The dog is much more away from this cluster, right? From these two. And when you are, so this is how each of these tokens are represented in the 2D form. This 2D two-dimensional vector is generated by reducing the 7 dimensions into 2 dimensions using a kind of lossy compression technique. Right, so we will not be discussing it here. Something like a principal component analysis, but not exactly, right? So this is a version, some technique, something like that. Right? So, and when you are converting the man and the woman, you can see that the king and queen, this woman and queen are at the same direction from man to woman. This is the vector direction. From king to queen, this is the vector direction. Right? So for that, and for the man to become man becoming royal, he becomes a king. The woman becomes royal, she becomes a queen. So this is the vector direction that a woman has to be moved to become a queen. So even with this two-dimensional representation, you can see there are some relationship with the location of each of these terms and their direction and the position compared to each of them, so that we can use some vectors, simple vectors at addition and deduction to have some meaning in between these terms when it comes to getting the meaning of the term. So unlike the one-hot encoding where you are just using a single one symbol to represent the location of the vocabulary, with these word embeddings, it contains some real physical meaning of these terms as well. So when it comes to real word embeddings, they are not generated like this, like manually adding some values for each of these terms. So there's a automatic way of generating the relationship between the other terms using kind of neural network training kind of, it's a kind of statistical technique. You can generate this word embeddings using a huge number of text fed into the machine learning system. So we will be not be discussing about these techniques in this lesson because it's too lengthy, right? So just remember that word embedding is a much more intelligent way of representing a token with a vector which has the real physical meaning or the real knowledge that particular token inside this particular word embedding. So word embeddings are much better when if we want to represent a token as a vector. So when you are representing a token, you can use the word embedding values like this. For the capital, you can have suppose the embedding size is 4, you can have this kind of vector for off. This is the vector. Sri Lanka is, those are the vectors. Those are just example values, right? So there's no real meaning, right? And we are training the an RNN network also. You can take the initial input vector as 0, 0, 0, 0. And for the next value, for the training value, you can get the for the x value, you can get the same value, and you are trying to predict the previous value. X1 equals y0, x2 equals y1, and so on. So you're with language modeling, what you are doing is you are trying to predict the next word of the token, right? Next word in the sequence model, and that is how you try to train the machine learning model, right? And once you have trained the language model, what you're going to do is you can use that trained language model to generate text. Right? So actually, these language models are very, very useful when it comes to doing many of the natural language related tasks like chatbots and sentiment generation, text translation, and many summarization and so on. And because of that, that's why we are much more interested in this language modeling task, right? So once you have generated the language modeling sequence model, what you can do is you can use some initial vector like this, right? So now you can see the notation has become somewhat changed, but this is the real notation that we have followed throughout this course, right? So in the earlier cases, we have just ignored the notations that we have used throughout the course, but here you can see the notations like angle brackets are used for the layer number, right? This is the activation for the first layer, for the second layer, third layer, and so on. T white layer, and these are the predicted values for the first layer, second layer, third layer, and the T white layer. These are the inputs, right? So for the initial input, we give some A0, some zero vector or something, and then once we generate some value with the trained model, you get some y1 hat input, and this y1 hat input is fed into the second time step, and it will generate the y2 hat. Y2 hat is fed to the third time step, which would generate y3 hat and so on. So until it is generating the end token or something, so like so which is another token, end of line or some end of text or some specific that kind of token we have defined in the language, where this is considered as the end of the text, right? So once this kind of token is generated, we stop generating from this model. So until that, we can generate the words from this model until we find this end token or some unknown token. So generally we have two separate tokens, specialized tokens generated in a vocabulary for end token and the unknown token. Unknown token is for the tokens that are not there in the vocabulary, right? So for the unknown token and the end token. End token means the end of the string token. So once the end of the string token is arrived, you stop generating the string. So then you can consider the words that are generated in each of the time step as the text generator. But this is how we generate some text using a language model. So this is easier to said than done, but with the current improved versions of sequence models, not using these RNNs, GRUs, and LSTMs, but with transformer models, which we are not going to discuss in the today's lesson. With these transformer models, it was very successful to generate new text that you see day to day using in ChatGPT and so on. Right? So that is why it is important to learn this how to what are the basics of generating these new tokens with a large, or not a large, but a general language model, right? Okay, for now, before we move into the advanced version of RNNs, let's see what are the problems or the limitations of recurrent neural networks. Right? The first thing is that the recurrent neural networks has a encoding bottleneck, right? So as we discussed, right? So let me draw it. So in each of the time step, we move the hidden state from one step to the other, right? But the problem is, although we are having many inputs, we are having a constant size we are maintaining for the hidden state, right? How long this would be, we still have a constant size hidden state. So whatever, how much the complex history that we have gone through, most of the information that we have learned would have deleted or forgotten when we are coming into this point, right? That is a major problem with RNNs, because the size of memory is only dependent on this hidden vector size. So this is acting as a bottleneck for encoding the information related to that particular context. The second limitation is that when you are learning this recurrent neural networks, as we have learned in the backpropagation of time, all the values are the red values are coming like this, right? That means the backpropagation information gradients are coming like this, and those are passed through the time up to the beginning of the time. So this is a very inefficient way of training a model, because at each of the step we have to consider each of these layers as different neural network layers, so that we don't have a way to make the learning process parallel. So you have to sequentially learn each of these layers or each of these time steps one by one to train a single epoch. So that is very inefficient when it comes to machine learning, because although this is not really a multi-layer learning mechanism, because this has multiple time steps, it has to wait until all the layers are trained through the backpropagation. So this has no parallelism, and we have to wait until all the layers are trained. So this is very inefficient and time consuming and computation hungry when it comes to learning. So this is another problem with recurrent neural networks. But not only with recurrent neural networks, but also the its derivatives like GRUs and LSTM, so which we will be discussing later. And the other main problem is that, as we have discussed, because one reason is the encoding bottleneck, and the problem is that it has RNNs, especially the recurrent neural networks, don't have this long-term memory. So because of the function that we are using in the RNNs to combine the hidden state and the input, the hidden state information get forgotten, right? It's forgotten exponentially with the number of time steps. That means it can't remember information more than 4 or 5 time steps into the history, right? So if you have like 100 or 200 time steps, it can't remember, RNNs can't remember the information what has happened in the history of 100 time steps. So that is a problem with RNN design. So these LSTMs, which are known as long short-term memory, and the GRUs known as gated recurrent units are developed to handle this uh, lack of long-term memory problem. So before we dive into the GRUs and LSTMs, just revise the uh, formula of the recurrent neural network. So in here, what we are focusing is the uh, hidden layer value or the attention layer value of an RNA. So this is also similar to the hidden layer value, right? So the hidden layer value is also known as the attention value at the layer at the time step t, right? So this notation is somewhat different from the notation that we have explained, right? But it is the same, right? So this instead of h, the hidden value, here we are taking the attention from the uh, teeth time step. So the hidden state for the teeth time step is also the attention of the teeth time step, right? So it is generated like this. So we take the earlier time step hidden value or the earlier time steps attention value, right? And the current input value, x value. And then we concatenate them together. And then we apply the multiply with the weight vector, or right? So in here we get a linear combination with these two, and then we add the bias term, right? So like we have discussed previously, like WTX plus B, this is the same thing that is happening, right? We take, instead of X, we have the concatenation of the hidden state and the X value, and then we do the multiplication with this vector WA and add the bias value, and then we apply the activation function G, right? So in general, this is not the sigmoid activation function, right? So generally we are using the tan H activation function as G, right? So this is the way that we represent the hidden state of a RNA. So we are not talking about the output is not relevant, right, for the RNN. So here what we are going to discuss is how the formulas of GRUs and LSTMs are designed. Right. So in order to understand it, so we have to clearly have some intuition of this RNN's hidden state formula. So if you are not familiar, just look at it and understand. So you get the previous hidden state activation and concatenate it with the input, and then we multiply it with the weight vector, and we add the bias. We get the attention function of it, and that is the hidden state of that particular time step, right? So in GRUs and LSTMs formulas, variations of this formula is used. So that is why it is very important to keep this formula in your mind, right? Okay. Now let's move into GRUs and LSTMs, why they are used, right? So GRUs are also known as gated recurrent units, are actually developed later in the time, right? So in 2000s, and the LSTM was invented in 1990s, right? So actually, LSTMs are larger in size and much more computationally expensive, but it is much more. It is capturing much more information. Right? So GRUs developed later to make it much more lightweight, right? So in GRUs, known as gated recurrent units, uh, are similar to RNNs, but instead of having the the output value in the RNN, so it has a little bit different name than the RNN. Is known as the cell state. Is represented by CT. So in RNNs, we have this hidden state defined by the activation of this particular of this layer, right? Of this is the activation of this particular layer of this particular time step. And for the GRUs, the value that is passing from this time step to the next time step is not known as the hidden step, but the cell state. Right? The advantage of cell state is that cell state is not getting updated too faster or with much frequency like in the RNNs. So the idea is that the CT or the cell state is getting updated only when it is required, when it is applicable to update it, right? So that means CT is only getting updated only when a significant change to the long-term memory should be happening. Otherwise, CT is not getting significantly changed. So because of that, CT or the cell state can maintain very important long-term memory, which the RNN can't keep, right? So in the LSTMs, it has both not only the CT cell state, but also the hidden state or the attention outputs as well, right? So in LSTMs, it has both ATs and CTs. In GRUs, it has only CTs. However, these formulas for GRUs and LSTMs are a bit different. The idea that you have to take is that because LSTMs have both ATs and CTs, it has much more higher memory footprint to keep the state inside the memory, because it has to keep both AT and CT in the memory. But with GRUs, it has to only keep the CT in the memory, which is equal to the memory requirement for the RNNs, where the AT is used instead. For the LSTMs, both AT and Ts and CTs has to be kept in memory to be used in the next time step. So if I remind you earlier, this the cell state in the GRU is the alternative for the hidden state in RNNs, right? For the LSTMs, it has both CTs, not only CTs, but the ATs as well. For the hidden state plus the cell state are available in LSTMs. So LSTM has so much higher memory footprint, and as a consequence, it's also better in performance as well, as people have found for most of the scenarios. So in practical scenarios of things like modeling the sequences of most of the stuff, like modeling the natural language, modeling the speech, modeling the some physical uh, phenomena LSTMs and GRUs work better when it comes to modeling the sequences because of the inability to keep a long-term memory. RNNs are not really used for practical implementation. So when you are designing a system, make sure that you are using either a GRU or an LSTM. So generally LSTMs are used first because this is the most widely used, most tested form of variation of RNNs. The advantage of GRU is it is lightweight, right? So you can use both. So generally people start with LSTMs and then go to GRUs if you want. Right. And one thing that you have to keep in mind is that because the architectures, the deep sequence model architecture that are relevant to see that are well known can be used for all the RNNs, GRUs, and LSTMs similarly, right? That means when you say this can be used for RNNs, generally they can be used for GRUs and LSTMs as well, right? So not in all the cases, but in many scenarios, when you are talking about the sequence modeling with RNNs, those things can be used with GRUs and LSTMs as well. So in the upcoming slides, we are going to discuss about bidirectional RNNs, recurrent neural networks. So although I haven't explicitly mentioned, that you can remember that when I explain this is how to implement bidirectional RNNs, you can implement the bidirectional GRUs and bidirectional LSTMs as well, right? So those are the real applications of bidirectional implementations, bidirectional LSTMs and bidirectional GRUs, because RNNs are not really used in practice for most of the practical requirements. So when we talk about deep recurrent neural networks, what we are actually using are deep GRU networks and deep LSTM networks. Right? So when we are discussing about attention models, we are about with RNNs, we are really talking about what we are really using in the real world are deep, what we are really discussing about are GRU attention models and LSTM attention models. Right? So RNNs are just used for learning purposes. Okay, now let's move to the formulas of GRUs and LSTMs. Actually, if I have started to tell about GRUs and LSTMs, that would be a very huge job, right? So it would take like a whole lesson to be covered for explaining GRUs and LSTMs, but I am not going that deep. But for your intuition purpose, I have just given the formulas used for GRUs and LSTMs, right? So you may think that those are very complex, but if you have understood this RNN formula very well, right? This formula, then you can easily understand what happens in this GRUs and LSTMs, right? So first, just look at the GRU, right? So this is the capital gamma, right? So this U represents for the update, right? Gamma U is for the gamma update. So what you do is you are concatenating the previous cell state CT minus 1 with the current input XT, and then we multiply with the update vector and add the update bias, and then we apply the sigmoid function. This is the gamma update. Similarly, we have this gamma R value, right? That means remaining value, I think. Yeah. So gamma R, which is we use the same previous cell state and the current input, concatenate them, multiply with the WR, the vector in the GRU, right? And at the bias of the bias BR and apply the sigmoid function. And this is the gamma R. That is how you retain or retain the value. So this value is relevant to the retaining value. This value is relevant to update in the value, right? So then what happens is you take this update value. Sorry, not this value. Sorry, this retain value. Then we keep it here, right? So you multiply the current cell state with the retaining value, right? So if you have to retain it, so it would be large in size, right? And then we concatenate with the input, like as usual. Then we can do the we multiply with another vector, weight vector, and add the bias, and then take the tan h. So that is the intermediate cell state. So this is not a cell state. It is an intermediate cell state, right? And what we do, how you calculate the cell state is we calculate the intermediate cell state multiplied by the update value, this value, right? And 1 minus update value, same value, times the previous cell state, right? So what it says is that if you want to update it only, this current intermediate cell state value will get updated as the cell state. Otherwise, if the update value is low, the previous cell state or the CT minus 1 will get prioritized, and this value will get assigned to the current cell state. So the cell state will not get updated unless this update gamma or gamma u is large in size, right? So this index is used for calculating this intermediate for calculating this intermediate value of the cell state, and this if gamma u is used for deciding whether the intermediate cell state should be updated as the current cell state or not, right? So in here, what it does is we say that the output value or the hidden state value is the cell state, right? So the AT is actually the CT in the GRU, but it is not the case in LSTM. In the LSTM, the same intermediate cell state is calculated, but not with gamma u or something, but just with the AT minus 1, the previous hidden state, right? So unlike this case here, the cell state is the previous hidden state, right? But in LSTMs, there's a hidden state and cell state separated, right? So for the GRUs only there is a cell state which is same as the hidden state, right? In here in LSTM, what happens is you calculate first you calculate the intermediate cell state like earlier, using the hidden state, the current input, and multiplied by a weight vector at the bias, apply the tan function, tan h, activation. Then we calculate the intermediate cell state, and then we similarly calculate the update value, update gamma forget gamma, and output gamma. So all those three are calculated using the previous activation or the previous hidden state, and the current, I'm sorry, all of them are calculated using the previous hidden state and the current input multiplied by these weight vectors. So those are different unique weight vectors at this biases, and applying the sigmoid function. Right? So whether to update, forget, or output is decided by this same operation. And what happens is, once you calculate the cell state, what happens is we take the intermediate cell state, C tilde t, and multiply it with update gamma. So that means if the update gamma is high, so this intermediate value will be passed to the current cell state. And if the forget value is high, that means if you want to keep the forget gamma, that means we want to forget the current value. So then the previous cell state will be passed to the current cell state. So there's a comparison between the current intermediate cell state and the previous cell state for to be assigned to the current cell state. Right. So that is defined by the gamma u gamma update or gamma forget. So once the C state or cell state is defined, that value is applied to the tan H and multiplied by the output gamma. So that means whether that should be given as the hidden state output, then only this activation value AT or the hidden state value will get updated. Okay, so unless you go through these slides very well and going through these formulas again and again and digest into your mind, you may find these formulas bit difficult, right? So that is okay, right? So just go through and try to understand it compared to the formula of the RNN. So you will understand this is not that difficult, right? So these GRU formula and the LSTM formula are defined using some small modifications to the RNN formula, right? So people have tried different formulas for different variations of GRUs and LSTMs, and those are the formulas that are remaining with the test width of time. Say right, those are remaining because those formulas are working, right? So maybe in future there may be better formula for or some different alternative than the GRUs and LSTMs, right? For the RNNs. So these are just two types of units that are advanced versions of RNNs that are used. So how they have thought about this, what were the intuitions of these units are something is what you have to know about, right? So once you have the intuition, how they have designed these GRUs and LSTMs, and then you can use it, and in future, maybe if you want, you may be able to design a new such unit as well. But in order to make it a better one, it should be having higher performance than these existing GRUs and LSTMs. So after people have tested with different formulas, these are the units that are remaining and accepted as useful, right? So that is why these two are remaining. So these things don't have any magic in it. people have tested it, and then they are keeping these. They say that GRUs and LSTMs are good, and these are their formulas, right? So just keep in mind, don't take it too serious. Okay. Okay, so now let's move into the another design architecture of recurrent neural networks, which is the bidirectional RNNs. So like in the, as I mentioned earlier, this can be also applied for bidirectional GRUs and bidirectional LSTMs as well. So the idea is that uh, in the pure form of the RNNs, we know, right? So once you have an RNN, so RNA sequence, the information is passed in a single direction, right? From 0, 0 to 1 to 2, and so on, in this direction only. So, so when you take this input, you have this input and this hidden state input, and that is how we create the output in this unit. So when you get this input and this hidden state input, that is how we create the output in this time step. In this time step, we only get the input from this time step. There's no, because there's no hidden input, we create some output. Right? So this is how the RNNs work. So the information is processed, the historical information is moving in this direction with the hidden state. In GRU, it is a cell state. In LSTM, it is cell state and hidden state both. Right? So, but in some scenarios, like natural language understanding, you may need to read a sentence not only in a single direction, but in both directions, right? Sorry, but in both directions. For example, if you want to read this sentence, like Colombo is blank of Sri Lanka. So we know the word that should come to this blank is the capital of Sri Lanka, right? But the problem is, if you have gone through these words from here to here up to now in this direction, you would only read like Colombo is the, but still you have no clue what should be there in the next blank, right? So if you have gone through from end to the beginning side in this direction, then you might have gone through Lanka Sri of, right, in this direction. So I know it's not intuitive to read in the opposite direction, but still, if you have learned a machine learning model to read from end to beginning, from right to left, so it would have the meaning like this is about something in Sri Lanka. So from this direction, you have got the idea like Colombo is something in Sri Lanka. So then you get the idea, okay, now this is relevant to this idea is, so what you have to fill is the capital of Sri Lanka, not something else. Colombo is of Sri Lanka in the other direction, Lanka Sri of, right? So then only you can understand, yeah, she's talking about the capital of Colombo is the capital of Sri Lanka. That's, yeah, now you know the word that should come to this blank is capital, right? So for that, you have to understand the sentence in both the directions, not only a single direction. Because of that, this is just an example that I have created, right? So there may be some better examples, right? If you want to find. So what I want to tell is that in order to understand natural language, you have to read from not only from left to right, read from left to right, but right to left as well, in order to get the meaning of a sentence or a paragraph or text, right? So for that, unidirectional RNNs, or the RNNs that we have learned up to now, are not sufficient. So you have to read from here, this side to this direction, and this direction to this direction as well. Because RNNs are defined only to go in one direction. What you have to do is you have to define 2 layers of RNNs. One of which of them, some of the RNNs are learning from in this direction, and another set of RNNs learning from this direction to this direction, from right to left. If you get the outputs from both of these LSTMs, then you have a much better understanding of the sentence, right? So there are 2 directions. So this is of learning. So that is why these are known as bidirectional LSTMs. So bidirectional RNNs. So similarly, you can define bidirectional GRUs and bidirectional LSTMs as well. Right? So what we do is we add 2 layers of RNNs that are directional in opposite directions, and then we give the same inputs for this for each of these layers, right? And then we get the outputs from both of these layers as the output from the bidirectional RNN. So that is the purpose of bidirectional recurrent neural networks, and this is there are some requirements for bidirectional RNNs as well, right? So when it comes to time series forecasting, you can simply use the unidirectional or single direction RNNs. But when it comes to understanding a sequence, like a word sequence or DNA sequence, something like that, maybe these bidirectional RNNs would perform better, right? That is why the bidirectional RNNs are popular for understanding a sequence when the whole data is available, when the complete set of events are available. So this is an example of bidirectional RNN. So we start from here and then we move in this direction. And there's another one set of RNN start from here and moving in this direction. All the X values are given as inputs, and the outputs are taken as the concatenation of both the outputs from both the units in the 2 directions. Okay, so that is about bidirectional RNNs. So now let's discuss about the deep recurrent neural networks. The problem is problem with the RNNs that we have discussed up to now was that those are too deep, but actually these RNNs are not really the deep neural networks, because there are multiple time steps involved in an RNN. They have to be learned as different layers in each of the time steps. But in each of the time step, it is learned as a single layer or shallow layer neural network. So means we are only using 1 or 2 matrix multiplications to get the final value. So those are shallow neural networks when it comes to a single time step. So, but although for training, we have to consider them as deep neural networks. When it comes to the performance, because the performance comes in a single layer, it can't handle that much complexity when it comes to a single layer or the neural network RNNs that we have learned up to now, right? But if you have the capability to add multiple layers of RNNs in real, that means for a particular time step, if you can have multiple layers of RNNs, then you can improve the uh, intelligence or the capacity of this neural network, right? So as we discussed earlier, because when we increase the depth, its interpretation capability or its functional complexity increases exponentially, right? So if you can add, instead of one layer, if you can add 2 layers or 3 layers, it can exponentially increase its uh, complexity of complexity or the understandable function if you can increase the depth. So it is very important if you can increase the number of layers of the RNA. So although we see them as uh, so so if you consider a single layer like this, right? We think these are just deep neural networks, but they are not, because in each of the layer, each of the unit, we have only one shallow neural network, but you can get the outputs from each of the unit and add another layer on top of it and add its value to the as the input to the second layer and get the second value output as the next layer input and so on up to the kth layer. And when we have backpropagation, when you do the backpropagation, we can move in the red line direction, red arrow direction, right? So it is much complex, right? So the depth increase in this direction, right? So when you, if there are no lines in between, so there are 3. So so this one is this generic one. So this one is a k depth. Depth is k, right? There are k layers of RNNs in this neural network. So give the inputs like this, and their outputs are given to the other layers, and those are also connected as RNNs from here to here and here to here and so on. And the depth is how many layers are there in, this is the first layer, second layer, this is the kth layer of the deep neural network, deep recurrent neural network. So you can, in this case, this is the y value that you wanted to predict, right? So because although this seems very interesting and very useful, because still there's a complexity due to the depth in this direction. When you add more layers in this direction, the complexity is getting quadratically higher, right? So generally, because there are many time steps in the recurrent neural network, it is not good to add many more layers on top of them. That means it is not good to increase the depth so much. Generally, 2, 3, 4, 5 layers, maximum 8 layers are used in, 4, 5 layers are used in recurrent neural networks or GRUs and LSTMs when it comes to sequence modeling, right? Because it is very difficult to train it, so it takes much time to see how much that propagation it has to do when it comes to training this kind of neural network, right? So it has to be moving from right to left and top to bottom at the same time when it comes to backpropagation. For the forward propagation, also the same, right? So it is very expensive to learn this kind of a deep recurrent neural network, but those are used in practice with less number of depths. That means for a small number of k values. Okay, now let's move into the, so before that, and also remember that not only for RNNs, but for the GRUs and LSTMs also, you can use deep GRU networks and deep LSTM networks as well for improving the expressive power or the function complexity that it is trying to model. Okay, so now let's move into the attention model. So this one is the most important or the most advanced version of sequence models. So, right, so this is in here we are going to give an opening to the modern sequence modeling technique, which is known as the transformer model. But in today's lesson, we are not going to discuss about transformer, but this attention is the birth of transform models, which are completely different from the RNN, GRU, and LSTM models. But so they actually the transformer was born with these sequence models, but after when the attention models are introduced to these RNN, LSTMs, and GRU models. So let's see what are these attention models. Say that your task is to understand a text using NLP, natural language processing, right? Also, natural language understanding, you are trying to understand. So when you are reading a text, right, you don't remember all the words in the text in your mind, right? So you can't remember everything that you have read up to now in your brain. So what you do is you only keep only the most significant or the important words in your mind, right? So when you are reading something, you only keep the important stuff in your memory, but not all the words, right? That is how you have improved your intelligence. Right? You only keep the most important terms in your mind, or you forget everything else, but you give the attention only to that, but only to a certain set of words, very few words that are relevant to what you are trying to understand from this text, right? So, for example, if I say that I went to goal in last year, so what you remember is that goal last year you went, so something like this. So what you understand is that you keep only the most important terms in your mind, but not the other prepositions and all the other garbage stuff, filling words that are in the text, right? So, but when it comes to RNNs or the LSTMs and even GRUs, there's no way of filtering out the most important time steps and having a more weight on these uh, terms, right? So that means uh, the near future or near past information will be preserved more, and the older they are, they would get forgotten. That is all about uh, long-term memory, right? Even with the LSTMs and GRUs, that's what we do, right? We don't give any specific uh, that means a weight difference or higher weight to only only to a selected set of terms or selected set of time steps, but we consider all of them the same, right? We update them, but we don't have a specific interest on specific terms or specific time steps. That is a problem when it comes to understanding understanding a text like a human being, because humans are understanding with attention. We are giving attention only to certain words, but not everything. So in attention models have tried to uh, learn a model like a human being, not like the existing RNN models. So this is what it is trying to do. So it is trying to, instead of, so those are bidirectional RNN units, right? So this is one direction and this is the other direction. So these are learning in two different directions. These are learning this direction, these are learning in this direction, but these outputs are not directly used as the output, but they are used for calculating a certain weight, right? So, and the real sequence is there in somewhere else. So this is the real sequence, right? So for all the terms x1, x2, xt, so there are x1, x2, y1, y2 to yt, right? So this is the real sequence. For this sequence, so this is a unidirectional sequence. In each of these sequences, we are using the outputs from these bidirectional layers as an attention. That means we use the softmax function. So I have not given the formulas for calculating these attentions because it's a bit difficult for you to understand because the time is also not enough. So you can calculate the attention and then you can find whether that particular, which term is, for example, x2 may be the most important term that should be used. So the x2 will be having a very high weight and this term will be highlighted when you are calculating this final vector that is propagating through this attention sequence model. So this is the attention model. So these are just some mechanisms that are calculating these attentions. So based on the T1, that means for the T time step, first unit, what is the attention? For this is AT1. So AT2 means for the T time step, what is the effect of second word, and so on. So we add all of them and then we have a mechanism to find which of the terms are more important. So in this case, for each of the terms, you have to do the same thing to add them and add to each of these layers. So this is quadratically complex. Quadratically complex means with the number of terms, with the number of time steps, this computation becomes quadratically expensive. That means if there are 2 terms, there it is 4 times expensive. That is, if there are 10 words, it is 100 times expensive to do this computation. But still, this attention model is very, very successful and accurate when it comes to making these predictions. So that is why this attention model has taken the attention of the AI scientists, and that it has become the prominent model of sequence modeling. And later, these RNNs, GRUs, and LSTMs were replaced with the transformer model with the paper known as attention is all you need. That means even these sequences, in these bidirectional sequences, and these sequences are not required. Only the attention is what really important. And the sequence of these terms has some importance, and that is also given to a transform model. But the attention is mostly important when it comes to making predictions. That was the finding in 2007 paper published by Google about attention is all you need. So that was the birth of transform models, uh, which gave the birth to ChatGPT and all the other large language models. So maybe in future we will be discussing about transform model and how it evolved with the power of attention. Right. So this is how we use the attention models for RNNs and GRUs and LSTMs. But later, attention, they have found that we don't need these models. We can directly use the attention and only some information about the positions of these words, right? Uh, and then these models would be working really well. So that was how the that was one of the uh, key advantage that are there in uh, the transformer model. So that's all for the today's lesson. Let's finish our discussion for that today. If you have any